Good evening, everyone. I'm Fredrik Horstedt. I'm Vice President of Utilization and Industry Collaboration at Chalmers University of Technology. And I wish you a very, very warm welcome to this Chalmers Lecture. William Chalmers Lecture. It was an event that really is a celebration of the birthday of Chalmers. That is the school, to keep in dear memory and to celebrate. The lecture regards, in fact, the inauguration of what was called Chalmerska Slöjdeskolan, the handicraft school. It was back in November 5th in 1829. This was 18 years after the donor himself passed away. The William Chalmers Lecture has been an appreciated tradition since 1991. It's a collaboration between Chalmers University of Technology, the Chalmers Student Union, and Chalmers Alumni Association. And let's hope that this is the first and last COVID-19 edition of the lecture. The lecture shall be held by a prominent Chalmers professor, and I am most happy to introduce this year's lecturer, Professor Erik Ström. Erik received his master's from KTH, the Royal Institute of Technology in Stockholm in 1990. He received his PhD from University of Florida in 1994, both degrees in the field of electrical engineering. He was first a postdoc and then assistant professor at the Royal Institute before he found his way here and joined Chalmers in 1996. He's been here, he's been a full professor since 2006. He is an appreciated line manager at his department. He has performed very well in, I would say, all core activities at Chalmers, that is in teaching, in research, and in utilization and innovation. In fact, he's probably the only person that I know of, at least, that has received Chalmers-wide awards in all these areas. He won the Chalmers Pedagogical Prize for excellent teaching efforts in 1998. He was given the PhD Supervisor of the Year Award in 2009, and he was awarded the Chalmers Area of Advance Award in 2020. He currently heads the Division of Communication Antennas and Optical Network. He is the current director of Chase On, one of the funding agency Vinnova's most successful competence center commitments. And from January 2021, he will lead the Information and Communication Technology area of Advance at Chalmers, the ICT area of Advance. So he's by all means a very prominent Chalmers professor, and I'm most happy that it is you, Erik, that performs this lecture tonight. Again, a very, very warm welcome to all of you. And with that, I leave the word to you, Erik. Take it away, please.
Thank you, Fredrik. Thank you, Fredrik, for those nice words. So today I would like to talk about a few things. So the first thing I would like to talk about is how to save the planet by being smart. Then I would like to embark on a historical expose of mobile communications from 0G to 5G and give a short outlook on 6G, what that is. And then, since this is a William Chalmers lecture, of course, we need a little bit of self-glorification and Chalmers high-fiving. So I will put that in to the middle of the talk. And then continue to talk more about a few things about being smart. In particular, we will talk a little bit about COVID-19 testing and the mathematical preaching of Reverend Thomas Bayes. And at that time, perhaps you have fallen asleep, so then it's time to wake up for a quiz talk, a little bit of quiz. So the quiz will be at menti.com with the code that you see on the screen right now. But don't worry if you don't copy it down now, it will be visible later on as well. Then I will switch gears and go to some pretentious social commentary. And sparkled through the talk, I will quote famous people to give myself credibility. And then at the end, there will be a Q&A session. So if you have any questions or comments, please put them in the chat. And me and my moderator here will be happy to discuss these. All right, so let's get started. Actually, when I was asked to do this, my initial title of my talk was on this. So instead of the word cocksureness, I had stupidity, because I think that's a central theme of the talk today, but also in the time that we live in. So we live in strange times. On one side, humanity has never been so well off as we are right now. We live longer, fewer people die now in conflict and war than for a very long time. But on the other hand, we see also big threats to our well-being. We see global warming, we see the overuse of the planet's resources, we see increased gaps between those who have and those who have not. So in short, we can say that our lifestyle as we have it right now is not sustainable. So the question is, how can we still keep some of our well-being and still be sustainable? So that's a question I would like to touch upon, and from my perspective as an engineer and researcher. So the problem as I see it is stupidity. We have stupid systems that leads to an unsustainable future. We have stupid systems for food production, stupid systems for transport, stupid systems for healthcare, stupid systems for energy, and stupid systems for production of materials and products we need, for instance, clothes. So the solution to this is, quite simply, we need to do things smarter. We need to have smart systems for food production, smart systems for transport, smart systems for healthcare, smart systems for the generation, distribution, and use of electrical power, and we need smart systems for production, for instance, circular production of textiles. And what is smart? What is driving all these things to become smart? Well, it's ICT, information and communication technologies. So what are those technologies? Well, on a very broad scale, it can be broken down as systems that operate in 4 phases. The first phase is measurement, collection of data. So we measure and observe the phenomena that we would like to control. So for instance, if we have a self-driving bus, it's important to know where the bus is located, where the road is, if there are people waiting at the bus stop, where other vehicles are, and how they are driving. To get this data, we can use sensors of various sorts, GPS, radars, lidars, cameras, and whatnot. So there are many options here. The next phase is to move the data from the collection point, from the sensor point, to the point where the data will be processed. It could be one point or several points, depending on the architecture. So this requires communications. So there are many options for communications. We have optical fibers, we have electrical cable, or we have wireless systems. So for our self-driving bus, for instance, we could have Ethernet, CAN, or FlexRay. All of these are electrical buses. Or we could use Wi-Fi, cellular communications, satellite communications, and so on. The third phase is about analysis. So when the data has arrived to the processing point or processing points, the data is then inspected, and with the objective to determine the next action. So in our self-driving bus, for instance, should we brake, should we steer, or should we shift gears? And the final part, the fourth thing we need to do is to act, that is to carry out the decided action. So this also typically involves communications from the decision point, where the data has been analyzed, to the actual device that carry out the action. So for instance, if we want to brake, we need to communicate from the processing point to where the brake system is located in the bus. So these things, measurement, communication, analysis, and action, is carried out in an endless cycle. So we measure, communicate, analyze, act. Things change, so we measure again, we communicate, analyze, and act again. A smart system like this can be taken even to the next level by introducing technologies that makes the system learn from its own experiences. And this is something called machine learning, which is a part of artificial intelligence, which is a buzzword at the moment. But let's now turn to communications, which is close to my heart since I'm a professor in communication systems, and it's also central for ICT system. At least it's in the middle of the acronym. So specifically, let's embark on a historical journey through time where we see how different generations of mobile phone systems have been developed and what type of services they have provided to us. So we know that radio communications and telephone systems has been with us for a long time. So radio systems and telephones were already operational at the end of the 1800s. But when did the combo arrive? That is, when did it become possible to make a telephone call from a car to a fixed landline phone? So let's explore that from the Swedish perspective. So among the early systems was MTA, Mobilt Telefonsystem A, which was developed by Televerket, the Swedish national telephone company, which does not exist anymore. So MTA was deployed in small scale already in the 1950s, and it was deployed in cars which were used by medical doctors. So this is an early application of what we today call mobile health or e-health. So the system MTA was followed by the system MTB. MTC was started to be developed, but was delayed and delayed and delayed. So a provisional system called MTD was deployed as an emergency solution. Anyways, the MTC development carried on, and it was eventually morphed into what's known as NMT, Nordic Mobile Telephone System. So the Nordic Mobile Telephone System is an early example of a first-generation system. So this is a 1G system. So MTA could be thought of as a zero-generation system. NMT is an early example also of an international collaboration to develop a standard. Here, the Nordic countries. So it saw the market in around 1980s, but as a curiosity, the first system went online in Saudi Arabia, which in many aspects is complete opposite of the Nordic countries. 10 years later, the second generation systems saw the market, and GSM is an example of such a system. So that was also developed in a European context. It was a digital system, which means that speech was first sampled and converted to ones and zeros before transmission over the air. It was foremost a system for speech, not so much about data communications. There was a texting service, SMS, developed, but it was not an initial hit at all. Support, however, for data communication, faster and faster, were introduced as the public started to use the internet more and more during the 1990s. But at some point, it reached the end of its development cycle, and the quest for higher data rates was not possible to do within the constraints of the standard. So about 10 years later, from the introduction of 2G, 3G saw the market. There were many such 3G systems. The most popular one, UMTS or WCDMA, was also developed in Europe. And 3G was developed now to give higher data rates. And one was thinking about what to use these higher data rates for. I remember myself, I thought that nobody in the world would like to have 1 megabits per second. What could that possibly be used for? But anyways, the search for a killer application went on, and this video call that this was thought to be a good killer application never really was a hit. Instead, mobile broadband, that is access, mobile access to the internet, became the killer application. So the access, not the application itself, was the most important thing. Again, 3G had some built-in limitations, which necessitated a new generation, 4G. So 4G was developed and put on the market about 10 years after 3G. There were a couple of these systems, and one example of those systems is LTE, which turned out to be the dominant one after a few years. So 4G was developed specifically as a mobile broadband system. So speech as such, talking in your phone, was not a special service anymore, but just just something that you could do either by switching over to 3G in your phone or as another service over IP. And now we're in 2020, and we see 5G being advertised and sold to us. So here there is only one system, so therefore there is not a strange acronym here, it's simply 5G. So this is also developed in Europe. So what do I actually mean when I say developed in Europe? I mean that GSM, WCDMA, LTE, and 5G, all of them have their roots from EU projects. So industrial stakeholders, that is manufacturers of base stations, telephones, and mobile operators, gathers in these big projects together with academic institutions, for instance, Chalmers and other schools, and they get together to build consensus on technical issues that needs to be standardized, things that basically says these are the things that the system needs to do in order to be interoperable. That is, one can use equipment from different vendors in the system. So it's in all stakeholders' interest to build a good system, to standardize the good system, because there will be no market for it otherwise. Therefore, it's possible for these fierce competitors, for instance, Ericsson, Huawei, and Nokia, to collaborate together in these projects, and collaboration is done in good faith and without any problems, not any big ones anyways. However, it's important that not the standard itself does not decide everything which needs to be done in order to make a system work. So once the standards have been settled, the vendors can go home and provide different technical solutions for this system and can compete with each other at a later stage. So what is new in 5G? Well, it's more of the same in terms of 4G, so higher data rates, better, cheaper, faster. But there are also two new important things, and these are two modes of machine-type communication, the massive machine-type communication and the ultra-reliable low-latency communications. And these modes, these services have been developed specifically to support demanding ICT applications. These applications that makes systems smart. So, 6G. So what is 6G? Well, let me tell you. The definitive, non-controversial answer to this question is that 6G is the system that comes after 5G. It's hard to be more substantial than that, since the first 6G EU project is just about to start. So things are a little bit unclear at the moment. There are a few things we believe, however, and I believe, and many with me believe, that we will see a continued push for using higher frequencies approaching the terahertz range. So this is a big technical challenge. We also think that certain services which are not ideal in today's systems will be developed. One such system is positioning. So if I have a device here, I would like to know where it is in 3 coordinates, X, Y, and Z, its actual position. And I would like to do that even when GPS is not available, like inside this lecture hall. Also, another thing I would like to know is how my device is oriented. Is it pointing up, down, left, right? Like this, almost like a compass, but in 3 dimensions. And the reason for this is, for instance, when we do navigation, the blue dot tells us where we are, but it doesn't tell us what is forward and backward. Right? So if we knew that, it would be easier. And I think you and I and many others have gone in the wrong direction and see the blue dot going in the wrong way before turning around and going the other way. There are many other applications that could be envisioned if we had this type of positioning technology. So anyways, we can assume then that the 6G technology will roll out in 8 to 10 years if history repeats itself. And I'm also very happy to announce that the Communication Systems Group at Chalmers will play an important role in this, the first 6G EU projects, which is just about to start. And this will continue our tradition to take part in these projects that started with 3G, 4G, and also 5G. So with that said, let's turn over to the self-glorification part of this talk. And let's talk about the research group that I belong to, Communication Systems. It was founded in 1993 by Arne Svensson to the left. And he hired 2 students, Anne in the middle and Tony to the right. And Arne, Anne, and Tony and others worked on 3G technology at the time, for instance, in the context of the EU project called FRAMES. So the group grew as time went by, and I was hired in 1996. In 2005, Arne became head of department and appointed me as head of the group. At that time, the group had 14 members, 4 permanent faculty, 1 assistant professor, and 9 PhD students. In 2018, I became division head, and Erik Ström took over as head of the group. So what is the composition of the group today? Here it is. Now, in my humble and clearly unbiased opinion, this is an amazing development into a truly excellent group. We are now close to 46 people, actually 46 people if you count them on this slide, but who tomorrow we might be 47, I don't know. So this amazing development is thanks to recruitment of great colleagues from all over the world, seniors as well as postdocs and PhD students, hard work, decent management, cooperation with industry and academics, both at Chalmers and elsewhere. So with hard work and the grace of the funding gods, we are now the largest group in our area in Sweden. And our area, by the way, includes wireless systems, 6G and such, but also many other things. Optical communications, hardware-constrained communications, cooperative systems, including positioning, vehicular communications, fundamental theory, and distributed information systems. So that about the group. So now a little bit self-glorification of myself. So I've been asked to be a little bit personal here, and what are my driving forces and so forth. And I did some thinking, and I think I have 2 driving forces. And the first one is the absolute joy I feel when I discover knowledge which is new to me, and sometimes also to others. And number 2, what I actually love is to share these discoveries and discuss them with students, colleagues, friends, and sometimes I plague my family with this also. So I've always been torn with the urge of solving practical problems, so go to the left in this graph, and I guess that's the engineer myself. I would like to work on problems that actually matters and matters now. But I also love theory for the beauty of it and the generality one can find in these areas. So, but I don't accept the fact that one has to choose left or right in this graph. And to prove my point, let's consider a quote of a famous person, Kurt Lewin. So Kurt Lewin was a German-American psychologist, and this is probably not an accurate quote, but it's a good one anyways. So he said, according to the quote at least, that there is nothing as practical as a good theory. And I think that's an excellent saying. So nevertheless, if he didn't say that, it's still a good saying. So when I'm faced with the fact to go for practice or theory in work, I actually don't. I go in the middle and try to combine theory and practice and try to find this practical theory that makes difference, both on a practical side, but also in a structured scientific way. So now when I shamelessly glorified myself and the communication systems group, let's change topic. Let's talk about a few things about being smart. Now, it's presumptuous of me to talk about this, so let's listen to what some famous people have to say about that. And let's start with Tage Danielsson, a Swedish author, actor, and director. And he said the following, he wrote the following in a book called Tankar från roten in 1974. So I'll put this up and I'll let you soak on the wisdom here for a few seconds before interpreting it. So what he said, utan tvivel är man inte klok, or in English, without doubt, one is not wise. So wise persons attach doubt to their beliefs. I think this is crucial. Nothing is 100% sure, ever. So for instance, if I say, I have COVID-19, then that is a statement of an unwise person. However, if I say, I think I have COVID-19, with probability 60%, then that is a statement of a wise person. So if I'm not happy with knowing something only with probability 60%, what can I do to become more sure? I can gather evidence. For instance, I can take a test, a COVID test, and then upgrade my belief if I have this disease or not after that. How should we then modify our beliefs when we get new evidence? So here we should follow the preachings or the mathematical preachings of Reverend Thomas Bayes. So Thomas Bayes was a Presbyterian minister, lived in the 1700s. And it's very doubtful that the picture to the left here is actually a depiction of Bayes, but this is the one you find when you Google him. So basically we don't know what he looked like. So the quote below is not an accurate one because it's been constructed afterwards from basically what he said. And it tells us how to update our belief in a statement that the statement H is true after observing some evidence E. Okay, so I won't go through the mathematical details here, but this is the equation that I will use in order to do graphs a little bit later. So let's go back to COVID-19 testing. So if we have an ideal test that gives error-free results, then we get a positive result if I have the virus. I get a negative result if I'm free of virus. So that means that the true positive rate is 100%, and the true negative rate is 100%. True negative means that I get a negative test result, and it's due to that I am free of virus. Unfortunately, no practical test is perfect. So in real life, the true positive rate is less than 100%, and in these cases, false negatives can occur. So a false negative is when we have the virus, but the test result is negative. And then the false negative rate is the probability of this to happen, and that is greater than 0. We can also, if we don't have a perfect, if the true negative rate is less than 100%, we can have false positives. And false positives is when we're free of the virus, but we get a positive test. Okay. For those who are interested in communication theory and so forth, recognizes this diagram as a binary, possibly unsymmetric channel, which we know quite a lot about. But that's a topic for another talk, I think. So, an example of practical numbers for a COVID-19 test are these, with a true positive rate of 98%, false negative rate of 2%, true negative rate of 95%, and a false positive rate of 5%. So these numbers are taken from a study on these tests from the UK this summer. The numbers are not super important, but they are in this range. The actual number actually on the test that you or I take depends on the quality of the test itself, but also with the skill that we carry this out. So for instance, I think it's reasonable to think that professionals, healthcare workers, do a better job at this than amateurs, the general public. Nevertheless, let's use this example for our quiz. So the quiz question is, if your test is positive, how sure are you that you have the virus? So I'd like you now to go to menti.com and enter the code which is on the slide here, or simply just scan the QR code to go there. So I give you a few seconds to do this. Okay, and maybe we can go over to the Menti slide, please. So we see some results coming in here. Some fairly low, a little bit higher. So the mean is now 77%. We're trending upwards. Interesting. So we have few results very far to the left, but most results are getting into the right here. Slightly faster than the US election. Okay. Maybe we'll stop at 80. How about that? There's still 77. All right. So we see here now that most people are in the high range here. 88%, 88.4. All right. Okay, so let's switch over to the slides again. Okay, so probably the reason for the high scores is that the true positive rate is quite high, 98%. So let me give you the answer. So drum roll please here. And I'm very pleased to announce that all of you are correct. So all answers are correct here because the question was not complete. So this quiz illustrates a common pitfall in forming beliefs after seeing new evidence, namely that we ignore our prior belief. What was our belief before taking the test? So let me try to illustrate that a little bit with this diagram. So on the horizontal axis, we have the belief that we have the virus before the test. On the vertical axis, we have the belief that we have the virus after taking the test. And points on the diagonal line, the diagonal blue line here, indicates our belief before taking the test. So say, for instance, that our belief is 50%. Then we would start at this point in the diagram. But if our belief that we have the virus is only 15%, we will start here in the diagram. So this is before the test, and actually we could be all over this place. I don't know what your belief in having the disease is. Now, once we get a test result, we need to figure out how should we change our belief. Then we go to Reverend Bayes and ask him, what should our belief be after the positive test? And he says, well, apply my theorem, and this is the curve you get. Okay, so now, if I'm starting belief is 50%, I observe that I get a positive test, then my new belief, my updated belief, is close to 95%. However, if I started at 15% and I have a positive test, then my belief is a little bit less than 80%. And both of these are quite okay. It just depends on where we started at. So we see that the difference between the starting belief and the updated belief is a gain in knowledge. So this is not exactly what we call information in information theory, but it's related to that. Now, the better the quality of the test, the bigger this knowledge gain is. And one could say like this, that some evidence gives a big change in belief, and some evidence give less change in belief. It depends on the quality of that evidence for the hypothesis that we are testing. Okay, now suppose I starting with a starting belief of 50%, of course I can also observe a negative test, and there's a corresponding curve for that we get from Bayes' theorem. So if we get a negative test, our updated belief should be quite low in this case. All right, now, so we have an initial belief, the blue curve, and then two curves, one curve that we move to if we get a positive test, and one curve that we move to if we observe a negative test. If we take repeated tests, we can simply trace out a curve in this diagram. So suppose we start with the starting belief of 5%, and we observe a positive test. Then our new belief should be close to 50%. Okay, so then after doing one test, and that test happened to be positive, we are at this point in the diagram. If we now take a second test, and that is also positive, then we move up in belief that we actually have the test, have the virus, which is natural, right? We have two positive tests. These tests also need to be independent, by the way. Okay, so if we're not really comfortable with this level of belief and take yet another test, and that turns out to be negative, then we should reduce our belief in that we have the disease, and actually we should reduce it down to where the 3 is in this diagram. And then if we take a fourth test, then again our belief increases. So we can carry on this until we are at the level when we're comfortably sure that we have a result that we can rely on. And what is the comfortable level? Well, it depends on the consequences of a decision that we take with this belief. Should we isolate, or should we have or what should we do, for instance? Now, this thinking can be generalized to any question that we can pose. So we can ask the question, is H, some statement, true? And then we can have the belief in that the answer is yes before seeing some evidence on the horizontal axis, and the belief in yes after seeing the evidence on the vertical axis. And we can trace out a curve in this. We can also generalize to the case where we have different types of evidence that tells us more or less about the question that we are asking. And then we can simply move to the appropriate curve when we see that evidence. So this process, if we apply that faithfully, we are rational and we are wise. We are updating our beliefs according to the evidence we see. And this is the best thing we can hope for. So this process will continue forever, could continue forever, and that's actually how the scientific method works. Right? Nothing is really 100% sure. We're always open to consider new evidence to update our belief about something. All right, so what can possibly go wrong here? Many things. So let's go to another smart person, Bertrand Russell. So he's a British polymath, philosopher, logician, mathematician, historian, writer, social critic, political activist, Nobel Prize winner, and a very active Wikipedia writer page that put on all these titles to him. So he wrote an essay called The Triumph of Stupidity that was published in 1993, and here's the quote from it. So the fundamental cause of the trouble, and I will return to what the trouble is later on, is that in the modern world, the stupid are cocksure, while the intelligent are full of doubt. And the word cocksure here should, in our context, mean that we have a belief without doubt. That is, we believe blindly that something is or is not, no matter the evidence. We can illustrate that in this diagram with 2 points of stupidity. We can either be up here, where we have 100% belief in something, or we can be down here, where we have 0% belief in something. And as a matter of fact, that's 100% believing in no as being the answer. So the bad news is that if we are in a point of stupidity, we can never move out of that using Bayes' rule. So no matter what the evidence says, we will not change our belief. Said in another way, we cannot learn anything new. And isn't that the definition of being stupid? The good news, however, is that for real-world problems, we can never move to a point of stupidity if we are not already there. That is, if we have an initial belief that is neither 0% or 100% and apply Bayes' rule in this diagram, we can never move to the point of stupidity. We could be arbitrarily close to it, but we will never move into it. So if we are initially wise, we're okay. Okay, so what is then the problem that Bertrand Russell is pointing for? So To give a little bit of context, this essay was written when Russell laments the rise of Hitler and the Nazi party in Germany. It was written in 1993. So unfortunately, the quote is valid already today, where we see a rise of anti-democratic leaders and nationalism, not least in democratic countries over the world. Remember that Hitler and his party became the biggest party in Germany during elections. So, although humans are not rational and we cannot really expect them to follow Bayes' rules, the problems of polarization we see today can somewhat be modeled by our diagram. So the root problem, as I see it, is that we, which I believe are intelligent, are full of doubt because we are fed with too much false and misleading evidence. So where does this evidence come from? Well, there are many sources, and I would like to discuss 3 today. So we have false evidence, false or misleading evidence that would lead us to have false beliefs. And this evidence can come from bad research or bad researchers, or a combo of these things, bad algorithms, or bad influencers. So take an example of each of these. So let's start with bad research and a bad researcher. So this is Andrew Wakefield, and he falsely linked measles, mumps, and rubella vaccination to child autism. And he published this in a very nice journal, The Lancet, which is a highly respected medical journal. So he gave in this paper, and still gives today, anti-vaccination activists misleading evidence that really pushes them to the brink of stupidity. There is overwhelming evidence for that vaccination is beneficial for public health. But this false evidence has clearly created problems. So my view on this is that one should please listen to the overwhelming evidence and vaccinate your kids. The paper, by the way, has been retracted by The Lancet due to scientific misconduct. So that paper is no research. It only has one place, and that is the garbage bin. We also have bad algorithms. So it's clear that if we're only fed with evidence that supports a certain belief, then we are enforcing our belief in that statement. So that could cause us to wander dangerously close to a point of stupidity. So how can this happen? Well, it can happen due to bad algorithms. So in particular, bad algorithms on our favorite social media platforms. We know that the social media platforms providers want us to spend time on their platform. And to encourage this, they have filter algorithms that connect us to people with the same beliefs that we already have and feed us with evidence to strengthen these beliefs. So we split out the community which has a heterogeneous view, a heterogeneous evidence, and heterogeneous beliefs, and form sub-communities which are enclosed in what we call filter bubbles. So these algorithms are very good at what they do, that is, to make us hang out on social media. However, they have serious consequences in that what they do to our beliefs, because they skew them in a way which is not correct from a point of evidence. Then we have bad influencers. So what is an influencer? With that I mean a person who has credibility in a community and use this credibility to influence people. And then you might say, hey, how about you? Well, I guess I could also be an influencer, me being a professor and a teacher. I don't know how much credibility I have in my family, but possibly my role as a father could also be an influencer. However, I consider myself as being a good influencer, of course. A bad influencer, however, is somebody who tries to use his or her credibility together with false or misleading evidence to influence beliefs that are beneficial to the influencer and not necessarily to the community. A typical example of this is a charismatic or authoritarian politicians that denounce all evidence that weakens his or her position as fake news. I think you know who I'm talking about. So what to do? I think we should always try to form our beliefs using Bayesian thinking. This is to be wise, and this is to be rational. We need to break out from our filter bubbles in order to get evidence that is somewhat consistent with the reality we live in, not only the reality as we perceive it inside our filter bubbles. When reading about research, we should take more trust in evidence provided by many researchers than by a small minority. Just because a researcher has said something, that should not be taken unconditionally as the truth. One should listen to many researchers. And then, of course, we should vote for politicians. We should not vote for politicians that lie, or at least lie too much, or are too cocksure in order to reduce their influence. But most importantly today, if there is anything I would like you to remember from this lecture, is that we should avoid the points to stupidity. Remember Tage Danielsson. Thank you so much.
Thank you, Erik, for a very interesting lecture that's given new insights and food for thoughts, and perhaps even challenged us a little bit.
Thank you.
And also to the audience, thank you for watching this William Chalmers lecture online. We have received some questions through the YouTube chat. You have taken a little bit of a philosophical stance in your lecture, but let's start out with a couple of a bit more techie questions. Like this one from the nickname Maker Mimo. Cybersecurity in 5G. Why do we hear a substantial increase in security-related concerns as compared to 4G? What is the departure from 4G introducing these new security risks?
Okay, I don't think there is new risks, but the consequences of security breaches is now more critical if we use 5G systems for these critical ICT applications that I talked about. So for instance, suppose we are using 5G for controlling vehicles, cars, self-driving cars. Of course, a security breach there is more has greater consequences than, say, if my Twitter account got hacked. So I think the security problems are the same. It's just that the consequences have now been are quite more serious. Therefore, one has to put more effort into this, I would say.
Okay, and what would the effort mean?
Well, effort means, for instance, to have a more secure environment. I mean, security is a big field. It goes everything from hardware to algorithms. So one has to strengthen up these things, in particular for those devices that will be used for these critical applications.
Okay. And what's your role in that process?
I'm not a security person per se, so I cannot really say this. My role is more to move the bits, not to protect them from security breaches.
Yeah, I read about you previously, and you have said that the technology that you are involved in developing can be used for both good and evil.
Of course.
And
yes.
What did you mean?
Well, I mean, for instance, if we think about 5G and positioning and things like that, it could be used for many good things, right? To locate people that are lost, for instance, or are feeling ill. But it can also be used to control people. I mean, control the activities of people, monitoring people and getting to this severe breaches of privacy that we see popping up over the world. So there is good thing and there are bad things in this.
And who should be responsible for how the tools are used?
Well, I mean, we both have a obligation as users of the technology to use it wisely. But I think then there is also a role of regulators. For instance, in Europe, we have taken steps to protect the privacy of users of the internet in general with the GDPR initiative. And things like that needs to be happening. But then also, of course, these companies who are using our data needs to step up their game in protecting us. So I think both the industrial sector, the legislative world and us as users have some work to do here.
Let's look at the YouTube chat again. There is a question again from Mecha Mimo, who's asking, are we going to progress at the same pace in the future as we did during the last 20 years in terms of the power and spectral efficiencies of communication systems?
Well, power and spectral efficiency, it depends a little bit on what we think about that. But if it's for a fixed power budget, we are probably close to the fundamental limits here. So to increase capacity, we need to densify. And we also need to have more bandwidth available. So the link to link, so from point A to point B, to improve that communication seems to be difficult at this moment. So we need to do other tricks to increase the spectral efficiency. Now, when we go up in frequency, as we have done now from traditional cellular bands to higher frequencies, we get more bandwidth, but that bandwidth is more difficult to handle. But once we learn that, we have more opportunities to transmit data, higher data rates, and we don't need to be super concerned about the spectral efficiency in these bands. Not at the moment, it will come later. But we, for sure, we have an unsustainable growth in data traffic on the internet as it is right now. So we need to do something about that as well. So became a long answer here, but we should use we need to use the bits that we are given in a more efficient way, and then given those bits, we should transmit them as efficiently as possible. We need to work on both.
Thank you. Myself being a consumer, how will 5G affect my day-to-day life?
Well, I know that Apple won't like me, but I don't think it will affect you that much. I think at the moment 5G is deployed at a rate. It will not replace 4G overnight, and 5G technology will be used in places where capacity is a problem at the moment. So there you would see a change as a consumer. But the big thing, I think, is these new machine-type communication parts that will change you, society, but not you as a consumer, end consumer.
You mentioned fake news earlier. Is it an adverse result of technical progress? Ethics and conduct should be thought of at the standardization phase of technology development.
Well, I don't know. I think for sure we can think of privacy enhancing technologies when we develop our technologies, for sure. But what is actually said over an internet connection would be very difficult to control from a technical point of view, and I'm not so sure we should as technology. That's more a legislative issue than a technical issue. So there is this freedom of speech versus using freedom of speech to hurt other people. There is this trade-off which is difficult to balance, of course. But circle back to the question, is there something technology-wise we can do? For sure we can do that a little bit in privacy-enhancing methods and so forth. Positioning, for instance.
But being a professor and researcher, what would your recommendation be to policymakers?
Well, to monitor this, right? And as Greta says, trust your scientists and talk to them and see what they have to say when building policies. And I think here, the good thing is I think Europe is a little bit more on the ball than in other places in the world.
Erik, this year's William Chalmers Lecture has come to an end, but before we end this broadcast, I would like to invite David Velander, Chairman of the Student Union, up onto the stage for a few final words.
Thank you.
Thank you, Erik, for this truly inspiring lecture. From the evidence that I have gathered, I conclude that you are truly a good influencer for both students and alumni. And once again, from the Student Union and the Alumni Association, a big thank you.
Thank you very much. Thank you. And thank you so much, everyone who has been watching.
Thank you for being with us and participating in the chat. See you again next year.